Morning, everyone. All doing well. Breaks were nice. Does anyone have any questions, concerns, etc. before we get started today? Alright. Couple reminders. We will have normal lab this week, so do report to lab as per normal. It will involve torque. So a lot of this sort of thing, or trying to level it, is what lab this week will be about. Now, for lecture today, the Friday before break, I'm basically going to be repeating what I did the Friday before break, because one lecture I had, enough people show up to actually do the lecture, but the second one I didn't. So if you were in attendance on Friday, or if you've watched the lecture recording from last Friday, then this will all sound familiar, and you have my permission to focus on something else. If you weren't here Friday, though, this will be new material. Basically, I'm going to try to speed through the last of the rotation stuff before we move on to something else later in the week. So just to address it, if you either were here last Friday or did watch the one recording I posted from last Friday. Now, the last Wednesday that I saw you, we were talking about torque, and we kind of ended on this image, talking about how this sort of a system could be possible. What was the conclusion that you guys came to about why this system, this seesaw with the kid sitting on it, is balanced the way that it is currently portrayed? The fulcrum is important, but the fulcrum is here. Normally, where is the fulcrum underneath a seesaw? The middle. That is not true in this particular case. So if I was to, again, to kind of show what we'll be doing in lab this week, take this meter stick. If my finger is what's acting as the fulcrum, for the stick to balance by itself, that fulcrum has to be under its center. If I move that fulcrum, kind of to replicate what's happening in the image, is it going to balance by itself? No. So, by moving the fulcrum, we have somehow introduced torque into this scenario. Even before you factor in that there's someone sitting on one end of the seesaw, when you move the fulcrum, suddenly it's not in equilibrium by itself and it starts rotating. And the reason for that is the mass of the meter stick itself, or the mass of this wooden plank itself, starts mattering if the fulcrum is not under its center. If the fulcrum is under its center, then the weight of the stick doesn't really generate any torque. And that's because, if you remember, the formula for torque is radius times force, specifically radius from the fulcrum. So if the fulcrum is underneath the weight of the object, that radius is 0. And therefore, the weight of the stick itself doesn't generate any torque if the fulcrum, if the pivot point, whatever you want to call it, is located directly under its center of gravity. All objects have centers of gravity. This is, we consider this to be the one spot within an item that its entire mass is centered around or concentrated around. For that reason, it's sometimes called center of mass. Center of mass and center of gravity are synonyms. I might switch back and forth between the two terms for that reason. And the general rule is, as long as something's center of mass is supported, it won't fall over, and it'll likely remain in rotational equilibrium unless some outside force is acting on it. For a lot of objects, center of mass is usually dead center, and that's why if I, again, support the meter stick at its center point, as long as the center of mass is above my hand, it's as if I'm supporting the entire stick at once. Because as long as you know where something's center of mass is, you can kind of treat it as just a point mass at that one spot. As long as that point has support, the whole item has support. It's the one spot where you can act on something, and it's like you're acting on the whole object at once. This means a few things about motion in general, but also for rotation. If an object's center of gravity is supported, it's not likely going to spontaneously start rotating by itself. You can still add outside torque to it to make something rotate, but if its center of gravity is balanced, kind of trying to show that here with this oil drum, then the object itself will kind of level out and not tip over on its own. This particular image shows a barrel of some sort. The center of mass of that barrel is dead center, which tends to be the case for most uniform geometric shapes made of one material. And I'm going to kind of replicate what it's showing with my water bottle here. If we just assume that this is a uniform cylinder, its center of mass should be in its center. So if I want to support the whole object, I have to make sure that its center is supported. And as long as the center is above my hand, it'll, even if I tilt it slightly, it'll usually tip back and support itself or stand up correctly. It only falls over if that center of mass is no longer above my hand. In which case, now the center of mass is at a radius from a point that it can rotate around, its own weight generates torque, and it spins away. Same kind of thing with this drum right here. But as long as that center of mass is supported, the weight of the object is considered supported, and it shouldn't start generating torque by itself. A very odd application of this is with these bird toys. Have you guys seen these before? Okay. Last group I talked to hadn't seen these, so I feel like it's becoming less common of a thing. That bird is, it's just a toy that, an old type of toy. When I was growing up, you could get them as very low ticket count prizes at like Chuck E. Cheese or something. And this thing is designed in such a way to move its center of mass into its beak. Because if this was all like solid wood, you'd expect its center of mass to be near its center, right? But the location of something's center of mass depends not only on its shape, what it's made of, but also where its mass is currently distributed. Kind of going back from the bird now, I'm going to look at this picture instead before describing how the bird works. This is a different toy that might be becoming less common. Is anyone familiar with the advertisement, Weebles wobble but they don't fall down? It's okay if you're not, I'm old. This object is designed such that it shouldn't fall over when you flick it or punch it. The same kind of thing is sometimes used for boxing dummies. The yellow parts of this particular item are made of a different material than the white parts. It's a little hard to see, kind of because the PowerPoint itself, the projector kind of grays everything out. But this part down here is likely made out of metal, whereas everything else is probably made out of some material that would be safer to punch if this was being used as a punching bag. And if that lower part is made of a heavier, denser material, it doesn't matter what the shape is, if more of the mass is lower down, then the center of mass is going to be lower. So an object's shape and mass distribution affects where its center of mass ends up, which for non-standard shapes and objects made of more than one type of material can kind of put their center of masses in weird spots. Humans are not made of one material, and we are not standard geometric shapes. So for most humans, your center of mass could be anywhere in your torso, really. In this case, since most of the weight of this punching bag is down here, that lowers its center of mass, and that makes it easy for this object to support itself. If you were to punch it to one side or the other, the center of mass is still being supported, whereas if it was up here, it'd be more likely to tip over because that center of mass would be further away from the axis of rotation. It would make more torque and it would be more likely to spin. But since the center of mass is lower, it's more easily able to support itself and stand back up. So again, the type of punching bag where if you punch it, it will come back, but then it'll fly right back upwards. The way this works for this old bird toy here is the bird itself is mostly hollow plastic, but they put weights, like metal weights, in the tips of its wings and in its beak to move the center of mass away from the body and put it right in the beak. And that's how, if you are physically holding it under its beak, it is able to support itself. Its center of mass is in its beak, so as long as you're supporting its beak, it doesn't fall over. Bless you. So an object's center of gravity kind of helps factor into how easy it is to make that thing spin. Most things, the center of gravity will be in its center, but sometimes you get interesting scenarios where that's not always the case. As long as the center of gravity is being supported, things will not spontaneously start spinning away on their own. All right so far? All right. Now, let's talk about how this matters for rotation. Tightrope walkers don't want to rotate off of the tightrope that they are walking on. So these guys don't want rotation to happen. They want to just walk in a straight line across the tightrope. Have you ever wondered why they hold that pole to be able to do that? Ever wondered what benefit that grants them if they have it versus not having it? I used to wonder that anyway. It's okay if you do. I'm the type of person that studies physics voluntarily. The benefit of the tightrope walking pole is it lowers your center of mass. For one, it distributes your mass further out from yourself, and the more mass you have, the harder it is to make you rotate in the first place. So by holding the object, you have more mass, and therefore it's harder to make you spin. But these things are never just solid pieces of wood. They usually have metal weights in the ends. You notice how they usually bend and don't just stay flat half the time. They usually bend downwards because the ends are heavier than the middle part. And if the ends are heavier and dip downwards, that lowers your center of mass, like the Weeble punching bag. The lower your center of mass, the less likely you are to fall over. So that's why they use these things. The lower your center of mass and the more supported your center of mass is, the less likely you are to fall over and the harder it is to make something rotate. Now, objects do generally still like to rotate around their centers of mass. This can lead to some pretty interesting rotations depending on where an object's center of mass is. For example, I'm not going to throw that thing. Instead, I'm going to throw this smaller ruler. If we consider this to be a standard geometric shape, it's all one material, so its center of mass should be approximately dead center if we ignore the hole in one end of it. And objects like rotating around their center of mass if they're going to start rotating. Outside of there being some other fulcrum, most objects default to spinning around their own center of mass. And so if I throw this thing in the air and let it spin, it usually should spin around its center. However, I can change the location of this thing's center of mass by adding mass to one end of it. This is just a metal clamp that I'm going to attach to one side of it. Now, it is no longer a standard geometric shape, nor is it made of all one material. There's a big chunk of metal on one side, and that has changed this object's mass distribution. If its center of mass used to be here, what direction do you think it has moved in if it has moved? Not a trick. I just like to get you guys to say it. How I'm holding it right now, would its center of mass be higher or lower than it used to be? Higher. And that's because there's now more mass up here. Physically, there is now more object up on the above part of this object, and that's going to shift its center of gravity higher because now the mass is mostly up here. It's probably fair to say that the metal clamp weighs more than this piece of wood. The center of mass has now shifted upwards, and now it wants to rotate about a different position. So when I throw it into the air again, it'll be a little subtle, so I'll try to spin it slower. Is it spinning around the center of the ruler anymore? No. It's now spinning around somewhere around here, I think. So objects prefer to rotate around the center of mass. If you know where that is, you'll know where the thing wants to rotate around. How this might affect your daily life. Objects with higher centers of mass tend to rotate more. This might affect you if you drive trucks regularly. They have more material higher up off the ground, and therefore their center of gravity is higher, they're more likely to wobble. The lower something's center of gravity is, the more stable it'll be. And the closer you're sitting to something's center of mass, the more stable you will be. So if you ever get airsick on a plane, try to sit as close to the middle of the plane as you can. Possibly right between the wings. Did I have one point? Oh, this also affects how a lot of tools commonly work in human hands. Because I mentioned this when I was talking about torque. Most human-built tools have something to do with torque and rotation. That includes the obvious ones like screwdrivers and wrenches that make something spin, but it includes more subtle things like swords and axes, because technically that's rotation if you're swinging something. And if you do ever have to handle an implement like that, knowing where its center of mass is can benefit you. Swords, their center of mass tends to be near the handle, but on purpose. And for that reason, it's usually easier to swing a sword than it is to swing an axe or a hammer, whose center of mass tends to be concentrated in the head of the implement, because that's where the big metal thing that you're trying to hit something with is. Come on. I swear I know how this thing works. Bless you. So if I move the center of mass back to all of one end, it's a little harder to swing for that reason. If you ever want to try this on your own, see how it feels in hammer configuration versus sword configuration, come give it a try. You can do something like that in lab this week too. Objects like spinning around their center of mass, but it's not just the position of the center of mass that they like to spin around. How you make something spin around its center of mass also matters in how easy it is to make something spin. Rather than throw the meter stick with a clamp attached to it, I am now going to start throwing this into the air, because this is a standard enough geometric shape. Just consider this to be a plank, kind of like I've drawn on the board now. It's all made of the same basic material, paper and cardboard. It's all carbon, so its center of mass should be in its center. That's the point that it likes to spin around. And to demonstrate that not only does the position of the center of mass matter, but also the orientation of the rest of the object, I'm going to throw this thing into the air 3 different ways, spinning through 3 different axes. I want you to notice the speed at which it spins each time I throw it. I'm going to try to follow along the way that I've drawn them here. First way I'm going to throw this thing, I'm going to spin it vertically through its middle like this, kind of like, I guess throw it like you would a pizza if you're doing that thing. So spinning through its center, through the vertical axis, rotating pizza style. Get kind of a baseline for how fast that spins. I am now going to switch to a different axis. The next one I've got pictured here has it spinning this way through the length of the object rather than through the vertical axis. So now I'm going to throw it like this. Try to gauge if it's going faster or slower. Faster. That's what you said, right? So, definite, it is faster. I want to make that point. Your eyes aren't playing tricks on you. We'll do it again and compare. First, pizza style. And then the second way. It's faster. Maybe not twice as fast, but it is faster through that axis. It's easier to make it spin this way than this way, even though it's the same object and the same mass and the same center of mass. And that's because the shape of the object, the orientation of its matter, also affects how it spins, or how easy it is to make spin. To kind of really drive the point home, I'm going to do this one more time through a third axis. I'm now going to do it like this, kind of the way that someone might kind of idly flip their cell phone in the air. At least that's how I used to do it. Don't though, you'll drop your phone like I do. But I'm going to do it like this, and I want you to see if you notice anything particularly different about this axis compared to the other two. I don't know why I insist on throwing things when I can't catch them. First of all, was that faster or slower than the first two? Slower. The object doesn't really like rotating this way, and for that reason, since it's harder to make it spin through that axis, it's going to spin slower with the same amount of effort from me. It takes more torque to get it to spin through this axis, and so it's just slower. It's resisting my attempts to make it spin. You notice anything particularly funky about this method, though?
Oh, you did something weird at the top.
Yeah, it does an extra backflip. I'm only throwing it like this, so it should only do this, but it kind of does an extra backflip once or twice as it reaches the apex. You ever notice that if you're flipping something similarly shaped to this? Again, your cell phone is the same basic shape, and it does it too. That is further proof that objects of this shape don't really like spinning that way. They will literally backflip and veer off course to resist your attempts to make it spin in this axis. To kind of, if you didn't see it, I'm going to try to prove it. This is official PC merch because of course it is. It's got Bluehost written on the cover there. And if it's not doing that backflip, when I catch this thing, the text should either be right side up facing you guys or upside down facing the board, right? Those are the only two options if it's only doing this. Sound fair? Now, I'm going to throw it, I'm going to catch it, and we're going to see what orientation the text is. I got to do it again. Ah, it did it. Now it's upside down facing you, which was not one of the two options. It did backflip. It spun in a way it wasn't supposed to. Again, if you're feeling brave, you can try that with your phone or a similar notebook. An object's mass configuration affects the way in which it rotates. And because we need names in math for everything. In physics, we call that an object's rotational inertia. Normal inertia, going back to Newton's laws for a minute, normal inertia is an object's tendency to resist changes in its motion in a straight line. Rotational inertia is an object's tendency to resist changes in its rotational motion. The more rotational inertia something has, the harder it is to make it spin. The less rotational inertia something has, the easier it is to make that thing spin. And any given object can have different rotational inertia values depending on the axis you choose to spin it through. If something is easier to spin a certain way, it has a lower rotational inertia through that axis. If it's harder to make it spin in that way, it has a bigger rotational inertia through that axis. Again, correlating directly to the more mass something has, the bigger its linear inertia, the harder it is to change its motion in straight lines. The more mass something has, the more force it takes to get it moving or to change its motion. Again, this correlates directly to the linear counterpart, linear normal inertia. To give a more practical demonstration of where this sort of thing occurs in your daily life, let us turn our attention back to the disembodied bike tire of science. Wheels are designed to spin. That's kind of their whole deal, right? And they're pretty good at it. If I take this wheel and I just make it rotate through its intended axis, it's a pretty straightforward and easy experience, in my opinion. It's not taking me a whole lot of force to do this. But that's not the only way I can make this spin, right? We live in 3D space. There's at least 3 different axes I could choose to spin this thing through. I could choose to spin it like a quarter, which doesn't go well because that's not the direction wheels want to spin. But I could. It's not nearly as easy. I'm having to exert probably at least twice the force to get it to move at a comparable rate of rotation. It does not like doing this. And that's why instead wheels are bolted like this to spin through this axis. The reason for this is spinning like this, less of the mass needs to move per second than like this, where more of the mass needs to move per second. Now, first of all, questions? Okay. Now, in physics, physicists, I forgot what I was for a second there. Physicists like having numbers for everything. I'm really only showing you these formulas to kind of illustrate a point. You don't have to memorize any of these. There's a page of these on your formula sheet if you ever need them. Because the orientation of an object's mass affects its rotation, physicists have different formulas to find the rotational inertia for every possible shape and axis that shape can be spinning through. On your formula sheet, there's a whole page of different shapes with different axes, all with slightly different formulas for rotational inertia. That I, by the way, is the rotational inertia variable. Tab back a sec. Rotational inertia, moment of inertia, variable I, uppercase English I, scalar, very funny unit that I don't like, that I wouldn't really require you to remember. It's a very weird one. Mostly talking about this to illustrate the point that the type of object affects how it spins. Kind of focusing on these 4 shapes here at the top. We've got a solid cylinder, a hollow cylinder, a solid sphere, and a hollow sphere. Based purely on their mass distributions, they can have different moments of inertia. They will be easier or harder to spin based on that fact. Again, you wouldn't have to memorize any of these formulas. They're in your formula sheet already if you ever need them. I might ask one question about it on the lab. Back page, by the way. Main point being, something's shape and the current axis you're spinning it through affects how easy it is to make that thing spin. Now, it's usually always a function of mass and radius. If they're hard to read on the board, I've got them rewritten over here. These are always a function of normal mass and also radius. They all have M for mass and R for radius. The idea being that the more matter something has in it, the higher its mass, the harder it is to make it move at all, either in a straight line or angularly speaking. So if you double something's mass, you double how much effort you need to make it spin. But the radius also matters, because that tells you how far the matter is away from the axis of rotation. The bigger something is, like the physically wider this cylinder or this sphere is, the further its matter is away from the center, and therefore it's harder to make it spin because you need more torque to make it spin. So they all depend on mass and radius, but sometimes there's an extra little fraction out front based on the shape, because sometimes a certain shape can cause the matter to be closer to or further away from the center just based on the shape. Just to illustrate this very briefly, I'm going to use these formulas and plug in a mass of 1 kilogram and a radius of 1 meter, just to try to show what I'm talking about. We take 4 shapes: the hollow cylinder, the solid sphere, and the hollow sphere. If we had 4 of these that were all the same mass and radius, they would all have different moments of inertia, different rotational inertias, because even the same M and R gives you a different number based on that fraction on front of the formula. The cylinder has a 1/2 out front. 1/2 times 1 kilogram times 1 meter squared is 0.5 for its rotational inertia. The hollow cylinder, if it has the same mass, which would be a little bit weird, they'd have to be made out of different things for that to be true. But if they had the same mass, that cylinder would have a moment of inertia of 1 instead of 1/2. And that's because if the cylinder is hollow, all of its matter is further away from the center. So if it had the same mass somehow, it'd be twice as hard to make that start spinning. And that's why, even though I grew up next to a construction site, so often me and my neighbor friends would see big concrete cylinders, like the kinds they put underground for plumbing and sewage before they got put underground. No matter how hard any of us kicked those things, they would never start spinning. And that's because if the cylinder's hollow, that kind of inherently puts its matter further away, and that increases its moment of inertia, harder to make it spin. Same kind of thing happens with spheres, whether they are solid or hollow. Solid sphere has a fraction of 2/5 out front, whereas the hollow sphere, its matter's further away, it's 2/3 instead. Now, this does assume the masses are the same. If you took a sphere and didn't change the material, you just hollowed it out, its mass should go down. So this is kind of they need to be made out of different things for this to work right. Main point though is where something's matter is affects how hard it is to make it spin. The more matter it has, and the closer that matter is to the axis it's rotating around, that drives down moment of inertia, drives up how easy it is to make it spin. I guess feel so far. Okay. Only one more thing I really want to go through, and I'll kind of draw us to a close with the rotational stuff for now. Last thing, kind of the thing that I've been building to all day. I've been going through all these points to kind of get to this last topic. The concept of angular momentum. Also rotational momentum, they would be synonyms. As we've been talking about rotation, I've been constantly trying to drive home that all the stuff we use for linear motion has some sort of a counterpart in the angular motion world. We talked about, linear displacement, velocity, acceleration. There is also separately angular displacement, velocity, and acceleration. Torque and force are angular counterparts. Mass and moment of inertia, mass and rotational inertia are angular counterparts. Momentum has an angular counterpart as well. Basically, linear momentum tells you how hard it is to stop something that's moving in a straight line. Angular momentum tells you how hard something is to stop while it's spinning. The more angular momentum something has, the more difficult it will be to get it to stop spinning. The less angular momentum something has, the easier it will be to make it stop spinning. Now, when an object has linear momentum, they tend to be moving in a straight line, and they want to keep moving in a straight line until physically you make them stop. Angular momentum indicates that once an object starts spinning, it wants to keep spinning. And kind of like how linear momentum dictates that something moving in a straight line wants to keep moving in the exact same direction without changing, the concept of angular momentum dictates that once something's spinning, it wants to keep spinning in the same direction, but also in the same axis without changing. Because angular vectors care not only about clockwise, counterclockwise, they also care about which axis they're rotating around, clockwise or counterclockwise. I could, if I use this as my axis of rotation, something could spin either clockwise or counterclockwise around it, but clockwise and counterclockwise around this axis is still technically different. So if something is spinning clockwise around the vertical axis, it wants to continue spinning clockwise around the vertical axis. And that's what angular momentum is referring to. To try to demonstrate, who knows what this is called? Starts with a G. Starts with gyro, ends with scope. It's a gyroscope, which is really just a scientific top, if I'm being honest with you. And I'm going to make this thing start spinning. Namely, this middle part is going to start spinning either clockwise or counterclockwise around the vertical axis, like how a top spins. And once it starts spinning in that way, I need a new gyroscope. All right. Instead, I'm going to use the bike tire. Which, if you're familiar with gyroscopes or anything that is gyroscopically stable, those objects are pretty hard to knock over. And that's because once something starts spinning, it wants to keep spinning in the same direction and around the same axis. So rather than the gyroscope, I'm going to do it with the bike tire. If I make this tire start spinning like this, that is currently rotating clockwise around the, let's call that the z-axis from your perspective. And so this wheel wants to continue spinning clockwise around the z-axis. It doesn't want to change either of those variables. It will not spontaneously turn around and start spinning counterclockwise, but it also doesn't want to change away from the z-axis. It wants to keep spinning around the direction the axle is currently pointing. And it wants that so badly that it will not tip over. This is what gyroscopically stable means. This rope is only supporting one side of it. The only thing keeping the other side up is angular momentum, it being very stubborn and not wanting to fall over. Notice as it slows down, it is eventually starting to tip. And that's because it's losing its angular momentum. It's losing what's keeping it spinning around the z-axis. And eventually, once it stops, it will hang like you'd expect it to. Once something is spinning, it does not want to change anything about its rotation. And this is why, if and when you ever learned how to ride a bike, you were told not to do this with your handlebars. Sound familiar? Because when you do this, the wheel doesn't like that. It fights you. It doesn't want to change axes that quickly. If you ever want to, not only are you free to swing the fake hammer around to determine center of mass, you are also welcome to hold this wheel and just try making it move. It doesn't like it and it will fight you, and it's a very weird feeling. Like, I'm not wobbling the wheel, I'm just trying to pivot it slowly, and it is resisting me. This is why tops stay upright, and this is why bikes honestly stay upright by themselves sometimes. If you get a bike moving, it can keep moving forwards without a rider, because the wheels don't want to tip over. It's also why unicycles work at all, because once the wheels start spinning, it also doesn't want to tip over. Now, these formulas down here, because we like math if you're in physics. These are just the angular versions of the normal momentum formulas. Normal momentum is mass times velocity, therefore angular momentum, which is L for some reason that was never explained to me, is angular mass, rotational inertia, times angular velocity. So, same formula, just with the rotational variables instead of the linear ones. And this formula says total initial angular momentum equals total final angular momentum. So this is just conservation of momentum again. Once a wheel starts spinning, it wants to keep spinning in the same axis with the same moment of inertia, and it doesn't spontaneously change its total amount of angular momentum by itself. Once it's spinning, once it has a certain amount, it wants to keep spinning at that same rate. Now, angular collisions, like we use the linear version of this to describe collisions. Angular collisions do exist, but they're kind of weird to talk about. So instead, I'm going to show a different application of this particular phenomenon. The idea that angular momentum is conserved in a process. Something's angular momentum level does not spontaneously change. It is possible to change something's moment of inertia in the middle of a process. And that's because moment of inertia depends not only on mass, but also on radius and the position of that mass. And if you are able to move a part of something, like a machine that's able to move some part of itself, or if you are able to move your limbs around, that means you are able to manipulate where your mass is at any given moment. I'm capable of taking my arms, and therefore the mass of my arms, and moving them from here to here. That takes some of my matter and moves it closer to my center of mass. So when I do this, I am driving down my moment of inertia, because whatever shape I am, my radius, the distance from my center to my hands, affects my moment of inertia. If I decrease my radius, I'm going to decrease my moment of inertia, even if I'm not completely one of these shapes. Pulling all my matter closer to my middle is going to cause my moment of inertia to drop, my rotational inertia to drop. Now, the conservation of angular momentum says that my total angular momentum is going to remain constant if I do that. If I'm spinning and I pull my limbs in, my angular momentum isn't going to change even though my moment of inertia changed. And what that means is, if my angular momentum stays constant, but my moment of inertia drops, my angular velocity has to increase to compensate. If I'm spinning and I pull all my limbs in, I decrease my moment of inertia, my angular velocity will increase to compensate in order to keep my angular momentum the same. You see this sort of thing in figure skating. If you've ever watched any amount of figure skating, have you ever noticed that they'll often enter a turn with their limbs out like this, and then they'll pull their limbs in and start spinning in place super fast, and then they'll throw their limbs back out and exit the turn? That's what's happening here. Their angular momentum is conserved, but they intentionally decrease their moments of inertia by pulling their limbs in. And even though I'm not a figure skater, I can replicate this in front of you. To try to exaggerate the effect, I am going to be holding these metal weights in my hands. So right now I have a certain moment of inertia if these are fully extended. I've got at least 2 kilograms of weight extended at this radius from my center of mass, and that has driven up my moment of inertia. And I'm now going to spin on this chair. So instead of figure skating, I have these weights extended. I'm going to spin in place on this chair, and once you guys notice how fast I'm moving, I'm going to pull all my limbs in like the figure skater does. This again should drive down my angular inertia, and therefore drive up my angular velocity if my momentum is conserved. Ready? I think I'm asking myself that mostly. All right. So, good gauge on my speed, and it's very uncomfortable. I don't know how skaters do it. You guys could see that, right? Okay. Good. So, angular momentum is conserved. If you change your angular inertia, odds are your speed is going to change to compensate. If I was able to somehow cut my moment of inertia in half, my angular velocity would double. You know, we can begin with the numbers next time. I've been talking a lot today already. So next time we'll do a little bit of math about that. Before we end, first of all, any questions from you guys? All right. Some reminders. Brain is braining. Lab this week, report as normal, especially make sure you bring your torque notes. The rest of this week, we're going to be changing gears. This is kind of the end of our rotational stuff for now, and for the next couple of weeks, we're going to be moving into more things about matter itself, and then pressure and buoyancy. Before that, we'll resume next time doing the math for all of this. I'll point out, though, just before we break, since the angular momentum is conserved, if you cut moment of inertia in half, angular velocity doubles, and the inverse would be true on the other way. If you double your moment of inertia, you'll cut your angular velocity in half. Even if you never figure skate, the last thing I'm going to mention is that this affects dizziness in humans. Because I've been led to believe what causes dizziness is your brain fluid spinning around your brain. Because if you start rotating, every part of you starts rotating, and that includes all your fluids as well. If your body stops, your brain fluid still has angular momentum, right? because it's technically its own object. It has its own momentum that's telling it to keep moving. So if you start spinning in place and then suddenly stop, your skull stops, but your brain juice doesn't. And so your brain juice keeps spinning around your brain. And that's what dizziness is. That in combination with the fluid inside your inner ear. It might be more the inner ear. Biology is not my strong point. But somewhere between your inner ear fluid and your brain fluid, something is still spinning even when your skull stops. And the best way to stop dizziness is to get rid of the angular momentum that that fluid has. And the best way to do that is to spin in the opposite direction. So if you're ever dizzy, try to figure out what direction you were spinning in, spin in the other one. Once or twice. Sound good? All right. If you don't communicate or have any questions, please have a wonderful day.